Welcome to the new era of video creation with BOC8. Today, we will discuss improving the interpretability of a deep learning model while maintaining its performance. How would you approach improving the interpretability of a deep learning model while maintaining its performance?
Model interpretability is crucial for building trust in AI systems, particularly in sectors such as healthcare, finance, and law, where decisions can have significant consequences. Interpretability refers to the ability to make a model's predictions understandable to humans. While high-performance models such as deep neural networks can provide excellent predictive accuracy, they often act as black boxes, making it difficult to understand the decision-making process. For AI to be widely accepted, it must be transparent and explainable, especially when the decisions can directly affect people's lives. This is also increasingly necessary due to legal requirements, e.g., GDPR's right to explanation. However, there is a common trade-off between performance and interpretability. Complex models often outperform simpler ones in predictive accuracy, but are harder to interpret. The challenge lies in finding the balance between maintaining high performance and enhancing the interpretability of the model. Deep learning models present specific challenges when it comes to interpretability. The nonlinearity inherent in deep neural networks means that the relationships between inputs and outputs are complex and difficult to represent in an easily understandable way. Additionally, the black box nature of these models makes it challenging to trace predictions back to specific features or data points, complicating the interpretability further. The overfitting problem can also affect interpretability. While deep learning models can achieve high accuracy on training data, they often overfit to noise, making it hard to understand which features contribute meaningfully to predictions. Moreover, deep learning often lacks strong theoretical guarantees, unlike simpler models like decision trees or linear regression, which come with more intuitive mathematical explanations. This lack of clarity makes it harder to provide clear justifications for model decisions, especially in critical applications. To address the interpretability challenge, several post-hoc interpretability techniques can be employed. These methods aim to explain a model's predictions after it has been trained. One popular approach is LIME, Local Interpretable Model Agnostic Explanations, which creates an interpretable approximation of a complex model's decision in a local region around the prediction. This allows for understanding the model's behavior for a specific instance, even if the model itself is a black box. Another widely used method is SHAP, Shapley Additive Explanations, which assigns each feature an importance value, based on the Shapley values concept from cooperative game theory. SHAP can provide insight into how much each feature contributes to the final prediction. Partial dependence plots, PDPs, help visualize how the model's predictions change with variations in one or more features. Finally, counterfactual explanations provide a way to explain model decisions by identifying the changes required to reach a different outcome. These methods can significantly enhance transparency. Some techniques for improving interpretability are built directly into the model architecture. For instance, adding a decision tree component to a deep learning model can provide a transparent mechanism to understand decisions. By training a decision tree as part of the network or as a surrogate, we can trace decision paths. In natural language processing, NLP, attention mechanisms have gained popularity, especially in models like transformers. These mechanisms show which parts of the input, e.g., words or tokens, are most important for the model's decision, helping to demystify its reasoning. Another way to improve interpretability is by calculating feature importance, which ranks input features based on their contribution to predictions, providing clear insight into which features are most influential. Lastly, global surrogate models can be trained to approximate a complex model and provide a simpler, more interpretable view of how it makes predictions. Sometimes the best way to ensure interpretability is to avoid using overly complex architectures in the first place. Shallow networks or simpler models often provide a good balance between interpretability and performance. For example, linear models like logistic regression or linear regression are highly interpretable, as they make predictions based on the linear combination of input features, which is easy to understand and visualize. Another example is rule-based models, which use predefined rules to make predictions. These rules are typically easy to explain to non-technical stakeholders. However, while simpler models may lack the power and accuracy of deep learning models, careful trade-off analysis can help determine when to use a more interpretable model without sacrificing essential performance metrics. Regularization techniques help reduce overfitting and simplify model architectures, which can improve interpretability. For instance, L1 regularization encourages sparsity in the model by setting certain feature weights to 0. This feature selection simplifies the model, making it easier to explain. Dropout is another technique that randomly sets some neurons to 0 during training. effectively forcing the model to generalize better and not rely too heavily on any one input. Weight sharing helps simplify models by enforcing certain layers to share the same parameters, reducing the overall complexity. Lastly, techniques like low-rank factorization can help in simplifying the underlying representations of the model, making it easier to interpret without sacrificing performance. Interpretability is not just about understanding model decisions, it also extends to ensuring that those decisions are fair and unbiased. One of the primary challenges in AI deployment is bias detection. It's essential to regularly check for any inherent biases in the training data or model predictions, as these can lead to discriminatory outcomes. Fairness metrics can be used to evaluate how well a model performs across different demographic groups. Ensuring fairness involves understanding where bias might creep into the model and implementing mitigation strategies. Explainable fairness is particularly important because it provides transparency regarding the sources of unfairness in predictions. Regular audits are necessary to track the fairness and equity of the models over time. To facilitate better model explainability, several tools and libraries have been developed to interpret deep learning models. For example, integrated gradients is a technique for visualizing how each feature in the input contributes to the final prediction by calculating the gradient of the output with respect to the input. Another tool is GradCam, Gradient-Weighted Class Activation Mapping, which is particularly useful for convolutional neural networks, CNNs, in computer vision tasks. It helps to visualize which regions of an image influence the CNN's prediction. Anchor is a technique for explaining classifier decisions through a set of simple rules. Finally, various fairness indicators help monitor and maintain fairness in AI models by identifying biases and measuring performance disparities across different groups. Ethics plays a critical role in model interpretability. As AI systems are increasingly used to make decisions that affect human lives, it becomes essential to ensure that these models are transparent and accountable. Ethical AI involves making sure that models are not only explainable, but also avoid causing harm or discrimination. A key issue here is accountability. Who is responsible for the decisions made by AI models? If a model makes an incorrect or biased decision, there must be mechanisms in place to determine who is responsible for the consequences. Moreover, bias and fairness in the model must be carefully examined from an ethical perspective, ensuring that training data does not propagate harmful biases. Finally, adherence to regulatory and ethical guidelines is essential to ensure that AI systems are developed and deployed in a socially responsible manner. In conclusion, improving the interpretability of deep learning models is an ongoing challenge, but is essential for gaining trust and ensuring accountability in AI systems. There are a variety of techniques available to improve model transparency, from post-hoc methods like LIME and SHAP to in-model approaches like attention mechanisms and decision trees. However, there is always a trade-off between maintaining performance and enhancing interpretability. Looking ahead, there will be continued research in developing more interpretable deep learning architectures and techniques. Additionally, ethical considerations, such as ensuring fairness and mitigating bias, must be prioritized as AI systems become more prevalent in high-stakes environments. Ultimately, the goal is to create AI models that are both powerful and understandable, providing clear insights into their decision-making processes.